Alright, so this is going to be video 8 of our parametric and polar review. Okay, in this video we'll be talking about area and arc length with polar. So we have our curve here, r equals 4 cosine of theta, and we want to find the area that it encloses. We find that using our integral here, the integral from a to b of 1/2 r squared d theta. So we're able to square r perfectly fine, right? That's no big deal. But finding our bounds is going to be something that it may be a little bit trickier for you. If we look at what 4 cosine theta looks like, okay, and this is why you need to really perfect being able to, just graph polar equations, okay? Because if not, you're going to end up kind of falling behind on some of this polar stuff. This is the graph of r equals 4 cosine theta. It's a circle with the radius 2, okay, because it goes out to, well, in Cartesian coordinates, this would be 4, 0. In polar, this is, well, no, this is still 4, 0 in polar. But yeah, so now we can figure out our bounds by, well, looking at this graph. This is going to be this is negative pi over 2, right? If we get negative pi over 2 here, all right, then we're going to cover all of this circle, okay? Because we're going to cover all these points right here, okay, that have angle measures close to negative pi over 2, right? And then that's going to go to pi over 2, right? It's going to cover all these angle measures that are close to pi over 2. Okay, so that's going to cover our whole circle. Area is going to equal the integral from negative pi over 2 to pi over 2 of 1/2 r squared. Well, that's just going to be 16 cosine squared theta. And then we have a d theta there. Okay? Well, we pull out the 16, pull out the 1/2, we're going to get area is equal to, this will just be 8, okay? This will be an 8 on the outside. We can also, since it says symmetry, we can integrate from 0 to pi over 2, and then just multiply the outside by 2, which actually can just get rid of this 1/2, and we'll be left with the area equaling 16, the integral from 0 to pi over 2, of cosine squared theta d theta. Now, to integrate this, remember, we need to use our half angle identity. So we get area equals, this will now equal 8, the integral from 0 to pi over 2, of 1 plus cosine of 2 theta, d theta, right? That's just our half angle identity. This would be over 2, but I already took it out, okay? Our area is now going to be equal to 8 times theta plus sine of 2 theta over 2, evaluated from 0 to pi over 2. Now 0, is that just going to kill everything off? It kills this off, and it'll kill this off too because it'll be sine of 0. So we just need to worry about plugging in that pi over 2, and when we do that, which is going to be 8 times pi over 2 plus sine of 2 times pi over 2, that's just sine of pi, and we know that that is also 0. So we're just going to get area equals 8 times pi over 2, so 8 pi over 2, which is equal to 4 pi. Now if we wanted to find the arc length of this function, okay, we want to find the arc length. Now we're just using this equation, okay, we're just going to be using our arc length equals the integral from a to b of the square root of r squared plus dr d theta squared, and then we have a d theta on the outside. Okay, now we can use our same bounds again, right? Our bounds aren't going to change. We can say that we have 2, the integral from 0 to pi over 2. Right? We have symmetry, so we can do that. And then we have the square root of r squared. What is r squared? Well, that's just going to be 16 cosine squared theta. Plus dr d theta squared, okay? And dr d theta, that is going to be negative 4 sine theta. Square that, that's going to be 16 sine squared theta. And like I said, we have a d theta on the outside there. Now, we have to go even further. We can pull out this 16, and we get a 4 on the outside. That can be an 8, the integral from 0 to pi over 2, of what? Well, this just becomes a cosine squared theta plus sine squared theta on the inside. That's 1, and that gives us just d theta here. So we get that the arc length is equal to 8 theta evaluated from 0 to pi over 2. Again, we're going to get that our arc length equals 8 times pi over 2, which, of course, we had that at the last one for our area. But our arc length will also equal 4 pi. Okay? Since this is a nice easy circle, we can actually just check our work here. Our area is pi r squared. And we know that our radius, well, what's our radius? Since this is 4, 0, our diameter is 4, but our radius is 2. Okay? So our area is 4 pi. Now our circumference is 2 pi r. We know, again, our radius is 2, so our circumference is 4 pi as well. So yeah, that's going to about do it. Now, your area integrals, they're not going to get too hard. Okay, you might have to do some calc 2 integration techniques, but really nothing too hard. For arc length though, arc length, that's, I would say, out of this section, our arc length integrals, they're going to be without a doubt the hardest, okay? And whether you're doing just a regular equation with x's and y's, parametric or polar, they can get fairly challenging at times, okay? Hopefully you'll get something that's not too bad, okay? You might get something that's just an inverse trig substitution, and that's definitely doable, but they can get out of hand at sometimes. I don't think you'll get that on a test because, like I said, like I've said before, there is a time limit to tests, so nobody's gonna give you a problem that takes an hour to solve, okay? But yeah, that's gonna do it for this video.
So if this video helped you, make sure to leave a like and subscribe by clicking my icon in the top left. You can also view the playlist for parametric and polar in the next video in the series. See you soon.